My name is Mattsson. I'm a professor in scientific computing at Uppsala University. I have some important things to say that I feel deserves some more spreading in the world. And that is this issue about infrasound. And wind turbines, they emit lots of infrasound. And the authorities in the industry claims it's harmless. I've seen opposite. We really need to stop and investigate really how dangerous this infrasound is. Infrasound can potentially spread at least 10 kilometers at levels that have proven to affect people. So I would say a safe distance is most likely 5 to 10 kilometers at least. In animal studies, they've seen that animals move more than 5 kilometers from wind turbines. So that's a strong indication that they don't like infrasound. We have measured where people live 600 meters from new modern wind turbines. And I should say that the larger you build them, the more infrasound you will get. And that is also something that the industry don't want to talk about. So I'm just saying, make a real study where you actually test the levels that we record, and they are quite high. So, and I will demonstrate what we have done, what levels we have measured, and also some references to new research that infrasound do affect people way below what you can hear. This is an important message, so yes, please share this data that I show you to others, local politicians, authorities, if you know people. I think this deserves more attention. Okay, so this is a short CV, just for the industry more, because they believe that I'm a prophet against wind turbines only. That is not true. So this is where I've been working. Since 2018, I'm a professor in scientific computing at Uppsala University. I did my PhD in Uppsala. I worked a few years at Stanford and NASA with air acoustics and jet engines and rockets and stuff, helicopters. I worked at the Swedish Defense Research Agency with underwater acoustics, methods to detect submarines, for example. And then I worked 1 year at the nuclear power plant. I'm definitely not against green, but my personal experience has made me more and more negative towards wind turbine. So it's based on facts and not religion. There are many waves in physics. So this is the things I've been working on for 25 years. These are partial differential equations. And the first two, Schrödinger equation and the Dirac equation. So the new Nobel Prize in physics went to things related to the first two equations. And I have actually been doing stuff related to what they got prize for, like tunneling effects. So I could spend the lecture talking about that also, show you some cool effects from quantum mechanics. I have been doing simulations on something called Bose-Einstein equations or solitary waves. And a tsunami is a solitary wave, for example. And I've been doing some work on Einstein's equations. So out in space, you have something called gravity waves. So those are quite interesting waves also. But I've also been working on acoustic waves quite a lot. I would say that most of my work has been in acoustics. PD is a partial differential equation. So that's what I'm a professor in. How to model reality with PDs and how to solve them. And the acoustic wave equation that we have based everything on is about acoustics. So if you're interested in acoustics, you have to solve the wave equation. So that's what we have been doing. We have a method called SPP-SAT. It's a finite difference method. You don't have to worry about this. It started in 1974 in Uppsala by Professor Heinz-Otto Kreis. It continued with a PhD student in Uppsala, and then the second PhD student in Uppsala, 2004, and that was me. And we have published 40 papers on this. I just want to briefly mention that there's a distinction between the generation of sound and propagation of sound. The generation of sound is very, very complicated. You have to solve something called the Navier-Stokes equations. It's very, very difficult. Then you have the propagation of sound. Once it's generated, it propagates. That's a much simpler thing. For that, you can use the acoustic wave equation. So what we do is we assume that we know the source, the wind turbine. This is how much sound it generates. It's a model. Then we can simulate how it's spreading. That's what we're doing. And the key point here is really that both the generation of sound and the propagation of sound is highly affected of the atmosphere. I will show you some examples. So one of the biggest lies from industry is that, well, these turbines are very not so loud. They have 105 dBA sound power levels. It's like a constant. And that's a big lie. It's not a constant. It can vary by more than 20 decibel, more, in a single day. And I will show you some results to prove this. So no, it's not a constant. So the biggest uncertainty in all of this is the sound power level. And the things that the industry, when you see all these simulations from the industry, they use, for example, Vestas data. This is how this new turbine, how much sound it emits. Then you put this into these simplified models, and then you get some contours. So here we have 40 dBA. No one lives inside. Fine, we can build. So there are many uncertainties. First of all, how much sound is generated. Second, how it's propagated. And in both these cases, it's not really reliable results. And I will show you some claim. So this is just an illustration that I always show to my students. So this is a volcano. I actually been doing some research on volcanoes and infrasound. So this is actually related to my research. But here we have the generation of sound. Here's generated.
Watch out for the shocks coming.
I have the propagation of sound in the atmosphere. So just to illustrate generation and propagation. So this is one of the main motivations that got me started 15 years ago, traffic noise. At that time, I was working also at the Swedish Defense Research Agency and working on methods to simulate underwater acoustics. And then we encountered these very simplified models like Nord 2000 that I will talk more about. And we wanted to test them, and they didn't work at all. In Sweden, it roughly costs 17 billion annually only in Sweden due to cardiovascular disease and reduced productivity. Not to mention reduction of house prices and stuff like that. But when it comes to wind turbine noise, it's quiet. They have different rules. Okay, so this is something I showed the Swedish Environmental Protection Agency in Sweden, 2012, where we actually did a careful check of the simplified models. So the blue line here is our model that we can prove is correct in this case. This is a benchmark problem. We compared it to two different parabolic equation methods that was published here, 2010, and we got quite similar results. Then we compared it to something called ray tracing methods, highly simplified models, assuming that the sound is high frequency, 1000 hertz, and it behaves like rays. So it's only valid for high frequency sound. And in this benchmark, it was a helicopter, 50 hertz, so it's low frequency sound. This is topography, so it's like some small hills. And this is something called transmission loss, how much the sound is reduced as a function of distance. You see, these ray tracing methods doesn't work at all. I spent 4 hours with 3 of my PhD students trying to convince the agency not to use Nord 2000 for low frequency sound. They didn't want to listen. We had a new meeting with them 3 years ago, and they still don't want to listen. So they will never listen. So this is a proof that this method, the Nord 2000 method, which is one of these methods, doesn't work. This is a colleague of mine at the university. He did some long-time measurements on wind turbines, 2014. And he proved that Nord 2000 model doesn't work against measurements. It's roughly 5 to 7 dBA too low values at 1 kilometer. All right. Okay, let's go to infrasound. Volcanoes, they emit lots of infrasound. And by detecting infrasound, you can model this volcano and get the feeling when it will explode by just listening for the infrasound. And nuclear explosions also generate lots of infrasound. High-speed trains and wind turbines. So there's a network in the world. It's called CTBTO. It's an infrasound network. So they keep track of nuclear explosions and other phenomena that happens in the world. So one of these stations are in Norway, in Elverum. So we've been there twice because these guys know infrasound, how to measure it. And unless you have been there and calibrated your equipment against their equipment, you can't measure it. We've been there twice and did careful calibration. So you're all familiar with electromagnetic waves, and you have different names. You have radio waves, microwaves, going up to X-rays and gamma rays. So those are electromagnetic waves with different frequencies. And the visible spectra is very narrow, what you can see. And when it comes to acoustic waves, you also have audible sound, roughly between 20 and 20,000 hertz, roughly. Then you have infrasound, that's everything below 20 hertz. You cannot hear it in the normal way, you can sense it. And then you have low frequency sound. I think in Denmark, they say 10 to 160 hertz. In Sweden, 31 to 200. So it's something that you can kind of hear. But infrasound, you can only feel it. Or some people can hear it. Here are just some human activities that will generate infrasound. There are many more. Here's some natural. Volcanoes, I already mentioned. But for example, tornadoes or storms generate lots of infrasound, or earthquakes. Meteor explosion. The northern lights also, actually. And then you have some animals that communicate with this. Infrasound from wind turbines are very different from natural infrasound. This is what it looks like. This is pressure as a function of time. It's like implosions. So every time the blade passes the tower, you get an implosion. This is what they look like in the spectra. So it's like small explosions or implosions. This is not what natural infrasound look like. Not at all. You can't hear infrasound from wind turbines, but that doesn't mean you can't perceive it. If you could, it would be like a dripping faucet that you can't sleep with, as opposed to sound of the ocean, which makes you want to sleep with the windows open. I think that's a very nice liknelse. I don't know the English word for it, but yeah. And then this was a really nice YouTube video that came a few years ago. Infrasound caused by industrial wind turbines. And many of the people that have done a lot of things in this area are in this video. Okay, so these are some questions that I get. For example, how infrasound is generated, how far it can travel, how much is lost to the ground and atmosphere. I will show you that. Interaction, how it penetrates building and affect people. And then how the atmosphere really, how important the atmosphere is for the propagation, but also the generation of the sounds. If you want to answer these questions, you really need to simulate this extremely accurately. And that is exactly what we have done. So the solution is something that we call SoundSim 360. It's just the software that is very, very, very accurate. And that can solve many problems in acoustics. So it's really 25 years of research in this. So it's not something trivial that you can use an AI to develop. It's really real physics in this. Okay, so these are some of the challenges in infrasound research and regulation, including low frequency sound. It's not only infrasound. So the biggest, I guess, is the reluctance from industry and authorities to absorb the research that is already there. They will not listen at all. And what I find really annoying is that they still use this dBA measure for low frequency sound. I will explain what that is in a couple of slides. And then the dependence on node 2000. And in Denmark use something even simpler, like the Danish model. That's just a log law. You have the similar in Sweden, but there it's called Naturvårdsverkets beräkningsmodell. So it's an ISO model. It's a log law with many parameters. Node 2000 is based on ray tracing with lots of parameters. And you can tune them. Depending who's running this program, you can tune it. You can get whatever you want with it. It's very user dependent. And the authority also claims that you can't measure infrasound. You can't measure sound. We don't trust that. They only trust node 4000 simulations. And the lack of research on this. a really lack of research here. But this is from a conference paper where they actually went for 2 megawatt turbines quite close to a house, 650 meters roughly. And this person had complained about this, and the authorities, of course, don't want to listen. No, it's way beyond the limits here, so it's okay. So Thomas and Bertil did a long time measurement. So first wanted to make sure what is the background noise when the turbines are not on. Okay, it's between 35 and 30 dBA, roughly. So this is a 2-week measurement. So I don't know if you can see it, but if you follow this green line here, that's the dBA variation, 2 weeks. This is the legal limit, 40. Almost all the time it's much higher. So up here it's 60. So you see the variation, how sound levels are varying with time. And this is a legit measurement. And since they were allowed to build these, Nord 2000 must have said that it's way below 40. But it's never below 40. Well, here. This is from January, 6 o'clock in the evening at Lagerstorp. You see this, the meter up there is close to 60. And this measurement is done correctly, with shielded from wind and everything. This is half an hour later at Snyggebo, also where people live, 1 kilometer away. Notice also the light. Imagine living here. The first I reacted on was the light, actually. But it's 60 decibel, 60 dBA. You hear this pulsating sound. This is not infrasound. This is something called amplitude modulated sound that happens in the evening. It's 60. The difference between 37 and 60 is, if you understand decibel, it's huge. All right. So this is a simulation that we did based on the measurement. So Nord 2000 here gave 37.6 at these 2 locations here. If we put this into our software and use the real atmosphere at that exact time, to fit the data, the sound power level had to be 128 decibel, not 106, to fit the data. The atmosphere has an effect on the propagation, but not that much. It might give you 5 decibel, but not 25. The rest is from the source. So these turbines don't generate 106 at that time. It's 128. And he did some measurements earlier that day. Then it was like 42, 43, the same day. So it can vary a lot during the day. Okay, so enough with that. So this is the building where we sit. I sit here. This is Ångström, Uppsala University. We had a rock concert here in August, here. So we wanted to simulate that. This is 50 hertz. So I just want to mention the physics here. If you want to simulate this, you have to really simulate it correctly, including the buildings, the ground, the atmosphere. And you have something called diffraction. Low frequency sound bends around corners. It also bends in the atmosphere. If you don't get that into the model, you can't simulate it. All right. We did a comparison with Nord 2000. In Sweden, they just decided to use Nord 2000 for everything. So this is 31 hertz. And here you see the sound levels. The black is the buildings. So this is the sound 2 meters below ground or above ground. Notice the difference here. Here and that here. So Nord 2000 don't have this diffraction. This is in 63 hertz, still low frequency sound. So this ray tracing method is completely off here. This is the difference. SoundSim minus Nord 2000. Red means more than 30 decibel wrong, too little. Blue is 20. So here you see the effect of using a useless method. Of course, close to wind turbines, you don't have so much houses. But here it's more obvious why it's not working. Okay, this is indoors, 200 hertz, 50 hertz. You see 50 hertz propagates through walls, through openings in doors. So this is the floor that we sit in, the building. Okay, here we put the source outside, 1 hertz, 100 hertz. So 1 hertz is very relevant when it comes to wind turbines. So this is the transmission loss, how much of the sound is removed. These walls, you can't see the walls here. Infrasound just goes through. There's no shielding against that. And this is a submarine outside the coast of Gotland. Just want to show that, yeah, you can do sound in the ocean also. Here it's really important that you get also the sediments in the bottom, because sound is going down in the bottom also. And this could be ships, boats, wind turbines offshore. They generate a lot of infrasound also, and low frequency sound. The reason why we wanted to go out and measure was to validate the model, to make sure it's correct. You have to do it against measurements. And then we went out to do measurements with this equipment. It's called Lidström. This is a highly accurate piece of work. It can measure infrasound only, down to 1 hertz. So we took this to CTTO to have it calibrated against their Hyperions. So it's very accurate at 1 hertz. Unfortunately, it cannot go below 1 hertz. And the highest levels are below 1 hertz. But then you need even more accurate equipment like Hyperions. And we have bought 2 of them. And yesterday we did the first measurement with them. So I actually had time to put it on the last slide. So it's really new. All right. So this is what the Swedish Environmental Protection Agency say, 2025. No special models are needed to calculate the infrasound from wind power, as this has been found in several studies to have no impact on humans. And then they list 4 references. 2 of the references are to their own reports. And these reports are not scientific reports. They're like, you can't even see the water. Then there's 2 real articles. 11 here. If you read this, it's like, yeah, it doesn't say anything. Available scientific research does not provide a definite answer about the question whether a wind turbine sound can cause health effects which are different from those of other sound sources. However, wind turbines do stand out because of their rhythmic character, both visually and orally. Okay. This study has not done measurement. There's no medical studies. It's just go through old studies. Then there's this Finnish study that they like to show that this is the proof that infrasound is harmless. Okay, what do? For 10 minutes, they expose roughly 30 people for 73 decibel infrasound at 1 hertz. 73 decibel. In total, if you sum everything up, here is 90 decibel. For 10 minutes. And Håkan was not invited in that study. Here, just some more references that I dig up, but I will leave it for Håkan. But an interesting study is already from 1985, where they actually did some testing on humans. So they found that 95 decibel infrasound, it's pressure. Then there's some new studies that show between 80 and 90 decibel, the brain picks up this, even though you can't hear it. So those are really interesting studies. And I should mention that in this report, the people who did these measurements got sick while doing the measurements. They got really sick. And the same thing happens to me in Courage when we go out. That's the reason why I'm standing here. Every time I go out and measure infrasound, I get sick. The day after, I get the terrible migraine, and then I can't sleep for a few days. That's why when I started to think, well, okay, some people say that infrasound can be dangerous or affect people. And then I found this article by Håkan. Then I contacted Håkan. And then I started to dig in the literature. And every time I go out and measure, the same thing happens. So for me, it's not a religion. I know it affects. Not all the people, but it definitely affects me in Courage and some other people that I talk to. And they report the same thing. So for me, it's a little bit personal. Otherwise, I wouldn't stand here and talk about it. Okay, so here are 5 serious deficiencies. So what you need to do is to do a study where you actually expose people to the true levels. And it has to be many test subjects, not only 30, it has to be probably 1,000. And you have to involve someone like Håkan in this study that knows something about the brain. You have to include people that are migraine sensitive, and it has to be long-term exposure, not 10 minutes. That's ridiculous. And to this, it's also that infrasound from wind turbines are pulsating. It's not natural infrasound. So personally, I believe it's this pulsating nature that makes it affect us more than the actual level. But that's my personal belief. And in many of these studies, you also see higher levels indoors than outdoors, because you also have vibrations with it. So this is probably very complicated. Okay, so this is from one of the measurements in December. It was very cold. It was blowing a lot. So this is a wind farm, Målarberget. So it's 27 turbines. You see a few of them here. Here is the equipment. We have 4 of these Lidström, and this is a windshield. This is how a windshield look like for infrasound. It's a metal. All right. This is from a measurement we did in October last year. We captured when they turned them off. Because the industry say you can't measure it. You only measure the background. Okay. This is when it's on. What you see here is the amplitude of the sound, kind of. Then they turn them off. And this is when they're off. On, off. In the same recording. This is the decibel levels off and on. So yes, it is the wind turbine that generates the infrasound. But yeah, you have 7 to 8 decibel at 1 hertz from just the wind. And in the Finnish study, they tested for 73. It's 99 at 1 hertz when they're on. So it's a big difference. It's 20 decibel. So, yeah, so yes, infrasound is caused by wind turbines. But you also have infrasound from the wind. But it's much lower, much lower. Okay, so this is something called Tersband, how you represent sound sometimes in frequency bands. 1 hertz up to 20 hertz. How much do you have in each frequency band? Okay, so you have on and off, and then you can decide how to represent the levels. You have something called dBA, dBc, dBg, and then you have something called dBz, but that's no weighting, so it's like dB. So if we sum all the infrasounds from 1 to 20 hertz, we get 106 decibel when they're on, 79 when they're off. In dBA, it's 22, or minus 2.8 when they're off. So you can trick with the numbers, use different weights. But this dBA, so if you look at, for example, 1 hertz, how much do you remove when you do the summation? Well, you remove 150. So if the wind turbine emits 150, it becomes 0. That's how it's working. So dBA, you can't use it for low frequency sound or infrasound. dBc is not very good also. dBg is often used. But yeah, it's not good also. For really low infrasounds, it's useless. Doesn't say much. So yes, don't use it. So this is from the measurement, the first measurement we did at Målarberget. So this is the measured value. These are 2 locations where we did measurements. Measured, calculated. So the deviation here between what we measure and what we simulate is roughly 2 decibel. Here. Here you have a resident. I talked to him. He don't feel very well. And he is very angry. Here he has roughly 95 decibel at 1 hertz. So everything here is at 1 hertz. 1 year later, we had 2 different locations. Measured, calculated. So here the deviation is roughly 1 decibel. So I would say it's quite good. Based on that, there's some uncertainties here. All right. So what we do is we do measurements. Then we take the real atmosphere at that exact time and put it into the model. And then we see how much sound is emitted from each of these wind turbines to fit data if you really resolve the physics very accurately. Then we get that the sound power levels here is 154 decibel, roughly. Here it was 155. This was in October last year. This was in December, 2 months later. We measured 115 instead of 99. So here it was much higher. It was more windy. It was cold. So yeah, it was much higher. Here you see the wind speed here. It was blowing also like this. Here you see the atmospheric effects. Why sound is propagating in the direction of the wind. So the levels to the right are much higher due to wind effects. Yeah, and here you can look at night and day, typical day, night and day. This is day, this is night. What happens is something called the boundary layer is compressed. Okay, it's physics. But this is also the reason why you get this amplitude modulated sound in the evening. When the blades are cutting through this boundary layer, that's when you get this terrible sound. And when you see something like this, that means that sound is bending down. Here it's bending down much more. So here just an effect of, here you see 1 hertz, 5 hertz, 50, 500 hertz. This is a wind turbine, 120 meters tall. And here we assume that the source level is the same for all frequencies, which is not in reality. Just to show the effect of the ground and the atmosphere. Here you take a real atmosphere, day and night atmosphere, 8 meters per second. This is how the sound at 2 meters above the ground looks like. How much is lost. This is infrasound. It's not lost that much. The yellow one is 500 hertz. So after 2 kilometers, it's more or less gone, except when you have this night atmosphere, you get this spreading from that. Yeah, so day atmosphere, night atmosphere with more wind. It becomes quite different how the sound is propagating and how much is damped. And here you have damping in the ground and in the atmosphere. This is what the sound looks like if you cut the slice. This is 5 hertz, 50 hertz. So at the night, the sound is bent down, so it's bouncing here. But it's damped also by the ground and by the atmosphere. And higher frequencies are damped a lot. Infrasound, not at all. So this is in a place called Åseda. This is where Kenneth lives. He has terrible migraine all the time. He can't move there. He can't live there. He asked us to visit and do measurements. And the industry refused to collaborate. That was an interesting episode. But we did simulations for him. This is a typical day, typical night, 8 meters per second. And they have the same wind turbines as in Målarberget, so we could use that sound power levels. This is what you get. And up here at B, you have Åseda. It's quite a big city, actually. So all these locations here, we have smaller cities. And these are the infrasound levels at these locations. So you see, Kenneth has 99 here decibel. This is if it would only blow 1 meter per second. Then it's not propagating very far compared to 8 meters per second. It's the same sound power levels. But the sound power level in itself also depends on the atmosphere. But the industry will never acknowledge that. So when it's blowing more, it's propagating further, but the level is also much higher. Okay, so the last slide is from Lervik, where Kjell-Åke lives. This is from his house. These are quite big turbines. The blades are 85 meters, 6.6 megawatts. He has 7 of them. This is last year in May. We recorded 105 decibel where he lives. This is what it looks like if we simulate it. This is a few months later. It was different weather. It was only 97 at that time. And this is an animation of this Lervik. So this we did this just to show the politicians because they like to have something looks nice. It's the same simulation. It looks nicer. So this is a big simulation of how infrasound is propagating. Here. And the last slide I added just before I went up here. I got it actually 2 hours ago. So we did the measurement yesterday with the new equipment that we bought. So we bought Hyperions, what CTBTO are using. So we went there in July to have them calibrated. So yesterday we did the first recording with them. Because the problem with this lead strum is that it can't go below 1 hertz. And the highest level is below 1 hertz. This is what we got. Sorry, this is from Leif. He don't know how to produce nice plots, but the yellow one is lead strum. So here it's at 1 hertz, then it drops. The other lines are the Hyperions. So the highest level is at 0.63 hertz, the blade passing frequency. It's roughly 128 decibel at that frequency. This is roughly 1.5 kilometers away. But I should say there are like 60 wind turbines close to this area. But this is preliminary results, but still, the highest levels is below 1 hertz. So of course we need to do more validation of this. But how much higher it is, we don't really know. But this is an indication that it might be quite high, actually. So you will hear more about that later. So thank you very much for listening.